Okay, we're doing experiment 8, which is a calorimetry experiment. And we're going to attempt to measure the specific heat of a metal. In this case, we're going to take a look at copper and try to compare the experimental value that we get to the actual value that we already know. Now, with most calorimetry experiments, we're usually looking at some unknown. We're looking at something that we're trying to measure compared to what we already know. And that's not what we're going to do here, but we're going to treat copper sort of as our unknown, as if we didn't really know what the specific heat was. And then to see how well we did, we're going to go back and compare it to the actual value. Now, with specific heat, we know that the heat added to any substance is equal to its mass times the specific heat of the substance times the change in temperature. So specific heat tells us how much energy per unit mass, per unit temperature, that material will absorb. Okay? So for copper, it is either 385 joules per kilogram degrees Celsius, that is our SI value for the specific heat, or if we want to put it into CGS units, we can write it as 0.385 joules per gram degrees Celsius. I'm going to choose the later because using grams is just easier since we don't have to make any conversions. Our scales already tell us everything in grams. Okay, now what do we have here? We have a system, this calorimeter, which basically has a cup which is going to hold the water. This is made out of aluminum. It's not very massive, but we have to include the mass of the cup and its specific heat because some energy will go into changing the temperature of the aluminum. The aluminum and the water are going to be at a lower temperature, so they're going to absorb the heat, and aluminum has a fairly low specific heat compared to water. It's 900 joules per kilogram degrees Celsius, considerably larger than copper, or 0.900 joules per gram degrees Celsius. Okay? So this is going to contain everything. This is what's basically holding the water, and it's going to also hold our copper shot. The water, of course, is going to do most of the heavy lifting here. Water has a very large specific heat, and therefore, when we are doing these calorimetry problems, it's usually the water which is either absorbing the most amount of energy or giving off the most amount of energy. Okay? 4,186 joules per kilogram degrees Celsius is the specific heat in SI. But again, I like to use the CGS units because we don't have to convert the gram to kilograms and then convert them back. So here are my known specific heats. I need these to be known values because I'm going to use these to obtain the specific heat of copper. Now, think about the calorimetry system. We have water, which is going to absorb heat. We have aluminum, the aluminum cup that's going to absorb heat. And then we have this hot copper shot, which I'm heating up, which is going to give off the heat. Okay? In a calorimeter, it's supposed to be an isolated system, which means heat absorbed by the water, okay, it's going to be positive. The heat absorbed by the aluminum, positive, plus the heat given off by the copper, this is negative heat, it's cooling down, should add up to be equal to 0 if no heat comes in or out of the system. This is not a perfect system, so there will be a little bit of leakage, and this will contribute to some of our uncertainty or some of our experimental error, but hopefully, because we started with water that's cooler and it's going to heat up by nearly an equal amount, we'll be okay. So if I take the heat of the water, the heat absorbed by the aluminum cup that's holding everything, plus the heat given off by the copper, it's actually negative heat, it's cooling down, this should all add up to be equal to 0. Now, writing HQ in terms of MC delta T, or MC TF minus T initial, it looks like this. My water mass times the specific heat of the water, 4186, times the difference in temperature. Finally, everything's going to come to equilibrium at the end of this experiment, minus its initial temperature, okay, plus the contribution from the aluminum cup. It's not going to be very large. the aluminum cup's mass, the specific heat of aluminum, the difference in temperature. It's going to be the same temperature finally at the end, the same temperature initially as the water. So I call both of these TW. Okay. Now I have my last term, the mass of the copper cup, the specific heat of the copper cup. This is what I'm trying to find here, folks. T final minus T initial. This is going to be negative, this delta T, right? Because my temperature of the metal is going to be higher than the final temperature. It's giving off heat. All this adds up to be equal to 0, okay? So I put my copper terms on the left. I put my non-copper terms on the right. So water and aluminum are on the right-hand side of the equation. I now solve for the specific heat, copper, and I get this equation right here. So this equation has the mass of the water times the specific heat of water, plus the mass of the aluminum times the specific heat of the aluminum, times the difference in temperature, okay? All divided by the mass of the copper times the change in temperature of the copper, okay? So this is the equation that I'm going to use. This is going to give me my experimental value for the specific heat of copper. At the end, I'm going to do a percent error and see how close we get to the actual measure. Now, this is a fairly crude calorimeter, so I hope to get below 10%, all right? But this actual value has been measured many, many times by very, very sensitive, well-designed calorimeters, you know, much more sophisticated than what we have right here. Okay, so let's look at the experimental setup. I'll turn on the lights. And allow the camera to readjust. Rotate over here. And now we are looking at the experimental setup. Okay, so what do we have here? Well, this is the insulating cup for the calorimeter. Okay, this is what we're going to place everything in and then allow it to come to thermal equilibrium. Okay, so how does this work? Here's the aluminum cup, which is going to actually change temperature. It sits in this ring. There's an air gap, so I don't have to consider any heat being absorbed by this larger cup. Then I put this cap on. I let it come to thermal equilibrium from there. Okay, so let's look at some of the different things that we need to measure. First thing I'm going to measure is I'm going to measure the mass of this aluminum cup. Okay, I put this on the scale. I get, okay, 50.6 grams. So this mass is 50.6 grams. All right. I am now going to begin to heat the copper shot, but I've already pre-weighed this. I know that this is 425 grams. This is going to be heated up, and then it's going to reach some temperature. Normally, if I'm running this experiment, I wouldn't add the water until the very end, but I'm going to add the water now. I'm going to tare this. All right, and I have exactly 175.6 grams of water. Okay, so this is going to go into my calorimeter. The initial temperature is measured. Okay, I'll let that come to thermal equilibrium. All right, and finally, okay, I get, I'll let that go a little bit further. Okay, we're down to about 5 degrees Celsius. So we'll see how that goes. So this is all set up. This is ready. I'm going to put this aside. And now I'm going to heat up my copper shot. See where that is. Turn this down just a little bit. It's bubbling over. And allow that to come into thermal equilibrium. While it does so, I'm going to stop this. I'm going to also, allow the water to cool back down because it's getting a little bit warm now. But I will get you the final results when we have them. Okay, we're back. We now have reached the final temperature where the temperature is not going up anymore. I made sure that my water remained cold, so I actually put it back in the refrigerator. And fortunately, it stayed at 5 degrees Celsius, so that was pretty good. So what I'm going to do now is I'm going to take the metal shot. You can see the metal shots in here, right here. And I'm going to add that to the water. And do this slowly so it doesn't splash. If I lose water, remember, that is going to be water that's not heated, and that's going to affect my final outcome. So I've emptied all the metal shot into my calorimeter. Now the copper is giving off heat while the water and the aluminum cup, to some extent, just the inner cup, just 3 different things interacting here, they're absorbing the heat. So let's turn off our water bath, and we are going to stir this around, see what we get for a final temperature, and hopefully the temperature is going down. Okay, I've added a little bit of uncertainty here because my thermometer obviously has some specific heat to it, but what I should have done is allowed that to cool first before adding this. But I get for my final temperature, okay, for my final temperature, that looks like it's pretty well settled at 21 degrees Celsius. So that's all I needed to do. I've taken the initial temperatures. The water was originally 5 degrees. The metal shot was 97 degrees. The final temperature after they both mix is 21 degrees. And of course, the masses, the aluminum cup was 50.7 grams. The water, I added 175.5 grams. I remeasured that after I made sure it stayed cool. And then finally, the mass of the copper was 425 grams. Okay. Let's pause again, and then we're going to take a look at all of these measurements and how they are combined into the equation. So here we go. We have our temperatures over here. The temperature of the metal was 97 degrees Celsius. So this is going to be the source of heat. The temperature of the water in the aluminum cup was 5 degrees Celsius. So this is going to absorb the heat. I got my little degree C right here, just so everybody knows I'm talking about Celsius. So the metal gave up the energy. The water in the aluminum cup absorbed the energy, and they came to equilibrium at a final temperature of 21 degrees Celsius. Okay? The aluminum cup constituted the least amount of specific heat here, or heat capacity is what I'm really talking about. At only 50.7 grams, the aluminum has a 900 joules per kilogram degrees Celsius. Specific heat, this is not going to be very much heat capacity, but we have to include that because it's going to contribute to the overall absorption of heat. By far, the water was most significant in absorbing the heat. Notice that I started at a much higher temperature, okay? I dropped 92 degrees from the metals. I'm sorry, take that back. I dropped 76 degrees to get to the final temperature, going from the hot metal to the final temperature, and I only went up about 16 degrees from the water's temperature. Again, the water, having a very high specific heat, takes more energy to change its temperature, so it's not going to change its temperature as much, okay? Even though there's much less mass. So there's the mass of the water, there is the mass of the copper shot. Here's the equation that I derived before. Remember, we need to know the specific heat of water and the specific heat of aluminum, 4.186 and 0.900 respectively for water and aluminum. They will go in this equation right here. Okay, so to calculate the experimental value, it is going to be the mass of the water, 175.5 times 4.186, plus mass of the aluminum, 50.7 times its specific heat, 0.900. Again, notice I'm using the CGS units, so I don't have to convert my mass. Times delta T for the water, its final temperature was 21 degrees. It started at 5 degrees. Now, don't get confused here. Here's the mass of the copper, but you switch TF and TM here, okay? TM is that initial temperature of the metal, which is the copper. I should have said TCU, but again, that's the initial minus the final. So this is actually negative delta T. But because of the way the equation sets up, you can prove it to yourself that it is in fact TM minus TF. So just be careful there, okay? So yes, this is your experimental value. This is what we found experimentally in the lab. And we're going to compare that to a known value, known specific heat for copper of 0.385 joules per gram degrees Celsius. So this is your accepted value that you're trying to compare it to. Okay? Good luck, fairly simple. We are only doing one metal. In the past, we used to use lead, but because of lead's toxicity, we've stopped using lead. So that makes your calculations all that much easier. You only have to do this one time. Good luck.